Meetup. And this is our today's schedule. I'm gonna introduce a bit about what is WebHack Meetup, and after that, I'm gonna pass to Paul to talk about a search engine design for logs from the ground up. At the end, we have a Q&A session and the networking session. And to begin with, we are WebHack Meetup. We've been hosting this event for over 3 years. And this one is our number 44 event. And we've been invite speakers from different backgrounds talking about different topics. And we've been hosting this event in different offices around Tokyo. And now due to COVID-19, we move every event online. So that's why we start to have our own YouTube channel. If you haven't followed our WebHack Meetup YouTube channel, please do it after the event or right now. And this video will be recorded and posted to the our YouTube channel as well after. And till now, we already have more than 1,300 members joining WebHack Meetup, and the attendance is even more than 1,800 people. So if you want to be the speaker, please fill in this form. I'm gonna copy this link to the Zoom chat later. And if you want to be a speaker, don't hesitate to fill in the form or just reach to us. And this is one of our sponsors. And you can use this HackMD to do the collaborative notes for today. And this is also the link. We're gonna share the link to the Zoom chat as well later. And without further ado, let me introduce today's speaker. And Paul is the CEO of Quickwit, and he has experience in search technology for around 10 years. And now he is also a maintainer of open source library. I don't know how to pronounce it correctly. Is it called Tentav? Things like that.
Tentav.
Tentav.
Tentav. A lot of people want to pronounce it Tentav, but it's Tentav.
Yeah, okay. Yeah, sounds good. And without further ado, Paul, please take it away. Thank you.
I'm gonna need the screen share. Yeah.
I just start share.
Hello everyone. So yes, today we are gonna see how we can build a cost-efficient search engine specifically for logs. It's not really logs, but I will explain that later. We have a lot of material to cover, so I will jump into the meat of the subject really fast. If you have questions, feel free to. I guess everyone can unmute their microphone, so feel free to let me know, and I can answer on the spot. Otherwise, there will be time after the presentation. So we can go very fast there because I already got introduced. I have my name is Paul Mazurel. You get my Twitter handle name and my email if you want to ask me questions after this talk. I have a little bit more than 10 years of experience in search engine, and I live in Tokyo. I worked at Indeed and Google in Tokyo, so some of you already know me. And while I was working at Indeed, I started this project called Tentav. It's a Rust search library. It's very close to Lucene, strongly inspired by Lucene. And I started this project because I wanted to make sure that I understood the inner working of search engine. And there's no better way to do that than to try to re-implement your own. The project got a little bit bigger. It got a little bit of attention, and because there was a traction this year, I asked two friends, Adrien and François, if they wanted to join me and create a startup, a search engine startup together. And so I quit my job at at Google last October and founded Quickwit with them. So we are gonna talk about all of our engineering ideas that spawned this project. So I don't know if you saw this Twitter meme last week. I thought it was very accurate. So regardless of whether it is a SaaS or on-premise projects, all of the logging related products that you know, under the hood, usually it's Elastic. And when it's not Elastic, it's Lucene. It's actually quite shocking. There is not much diversity in this space. Everything is based on Lucene or even Elastic. I love Elastic. I think they do a great product. I really love Lucene. It's awesome. It's a principal source of inspirations for TonTV. But I think the architecture is not really well suited for one type of search. I'm gonna explain what I mean by that. So if you were to consider all of the search engines that you interacted with as an engineer or even as a user, if you were to plot them on a scatter plot with the number of documents on the x-axis and the number of query per second, so the amount of traffic it gets on the y-axis, it will probably look like something like that. So you can put, mentally, you can put your own company, because I think there are a lot of search engineers in this meetup. So Mercari is probably somewhere here, I guess. I could be wrong. But yeah, you can put all of them, and you will see that there is basically two big groups. One group that I will call public search. So Amazon, Google, Indeed, Wikipedia, Twitter. It can be a smaller service, something that gets less QPS, it doesn't matter. It will be on like this group. And then you have something that is private search. That's your Gmail account is a private search. And the log search that you have in your company, it's gonna be also a private search. The intranet in your company, it's also a private search. And it's really a clear, like there is a clear separation here, because imagine it's a log scale, so you can easily write a line here and get the two groups. So what's so different about private search? So what the obvious from this chart is that you have a lower QPS per document ratio. So as a result, a simple result, you cannot neglect the cost of indexing. That's something that we will have to keep in mind, but there are other implications as well. And another thing that we often observe is that usually you are in a multi-tenant setting or akin to multi-tenants. So let me explain that. Of course, if you send your logs to a company like Datadog or something like that, they have multi-tenancy, which means that they host logs of many different people, and when you use it, you only search into your logs. But even if you use like log search on premise, it's also in a sense a multi-tenant setting, because every single microservice in your company has its own index, and it's basically the same problem. Maybe security is not as much an issue there, but in terms of performance and cost effectiveness, it's exactly the same problem. So now that we know our targets, yeah, let's build the 10x more efficient search engine for logs.
Sorry for interrupt. If you want to use the cursor, probably now it's not visible to us if you are using the cursor. So probably not full screen is better.
Not full screen is better.
Okay.
So
yeah, we can see your cursor right now. Now, yeah, your cursor is showing.
Okay.
Yeah,
can you see it here?
Oh yeah, no, it's fine too. Yeah, great.
Okay. It's just that I was putting it on a different screen.
Okay, thank you.
Okay. Yeah, so let's go through different ideas that are bringing our costs down. So first, we use Lucene is using Java, and that's kind of a low-hanging fruit. We use Rust and we use TonTV. Lucene is awesome, but TenTV on an open benchmark that you can run on your own hardware typically clocks 2 times faster than Lucene, so that's some savings there. Also, well, Java has a GC. GC is nice when you want to maximize your throughput, but in a distributed search setting, usually you dispatch your query among different nodes, and your query time will be as slow as the slowest of your nodes, right? So you want to have the lowest variance possible, and Rust typically gives you very stable performance, whereas Java has a little bit variance. Also, I must say that Lucene is awesome, and, and they do a really good job at not having too much stuff to garbage collect. So yeah, first thing we do, we use TenTV, and once again, I love Lucene. You will never hear me saying bad thing about Lucene. Another thing where we can save a lot of money is compared to Elastic, at least. Solar is different, but Elastic does document replication. What it means is that when you send a document, it's sent to a primary node, and the primary node is in charge of sending the document to the different replica in the replica set. So let's say that we have 2 replicas, that's 3 nodes, and the indexing will happen independently on all of the 3 nodes. So we do the indexing 3 times. That's a low hanging fruit for us. So we said that for private search, indexing is not considered super cheap anymore. One thing that we can do that is simple is index first, and then we can replicate the index. So I wrote segment there. Segment is just like a piece of index. Let's index, and then we copy the index instead of copying the document and indexing everywhere. So I'm gonna skip a little bit there and go to the conclusion. But when you run indexing, you are trying to maximize your throughput. You want to get the maximum document per second to index for your hardware. And a good indexing machine is one with a high load factor. So you want your CPU to be at 100% all of the time, basically. Search is a very different game. It's a latency game. You're trying to make sure that your 90th percentile is not bad, and your search time is stable and low. For this, you never want to have a super high CPU load time because it sends your 95th percentile very, very high. So as a solution, we actually want indexing and search to be on different hardware. That's also an easy thing to do. So that's our low-hanging fruit. And now we get into the fun stuff, the complicated stuff, the exotic stuff. And it's gonna be about multi-tenancy. So I'm not sure, I used the word before. I'm not sure if you guys are familiar with the concept of multi-tenancy, but it's very simple. If you want a car, but you cannot afford a car, one thing that you can do is notice that you won't be using your car all of the time. Maybe you only use it a couple of hours in a week. So what you can do is that you pay a car share service, and when you're not using your car, somebody else will be using it. And so the promises of multi-tenancy, like a good multi-tenancy system, it should be cheaper to share your car with other people. And the second thing is it should be totally invisible to you that other people are using the car. So in the physical world, usually you have a lot of leaks, like maybe like you end up with potato chips in the car, or maybe it smells bad, or or whatnot. In the IT world, we usually expect to be able to make things entirely invisible, and you never realize that when you're on Gmail, somebody else is on Gmail using the service as well. So we want to have this experience. And we will see that in the next slide that the architecture used in Elastic is, and basically every single search engine out there is not very good at dealing with multi-tenancy and offering the first part of the promise. which once again was reducing your cost. So sharing should reduce your cost. So this architecture is called the shared nothing architecture. It's something that became really popular in the 80s. And the idea is very simple. You split your dataset into smaller parts and you dispatch them among your nodes, and your nodes will be dedicated to like this subset of the data. They will only do compute on their own little subset. So they don't share their memory or they don't share their storage. They just work on this piece of data and other people cannot access them directly. That's it's so common that you probably have never seen other kind of architecture. So you see it in Cassandra, Elastic, MongoDB, blah blah blah, almost everything. It's for most use cases it's the best architecture, so that's why it's so popular. The idea, the most important benefit is actually for transactional payloads. It's better in terms of locking because you hold the lock on the node that owns the data, so it's much better. There is no need for a shared lock for that. But we don't care about that in search. In search, the story is more about moving the data. So the idea is really simple. You want to move the query to the compute, to the data, rather than doing the opposite. And if it was not clear enough, it's just the query is really small. So you send the query to the different nodes, the data does not move, the computation happens there, and then you send back the result, and hopefully the result is much smaller than the data. So it absolutely makes sense. It's really that simple. So one thing, once again, this is the best architecture in almost all of the case. One thing that we can point out to explain that maybe today it's not as critical as in the 80s. In the 80s, if you had a server in a data center, usually, or you had it on premise or whatever, usually the network you would have access to will be of 10 megabit per second. Nowadays, a good node on AWS is usually 1,000 times faster than this. So like moving the data, it's something that we can consider today. It's still not a good idea for most search, but it's something that at least we can consider. So yeah, let's come back to multi-tenancy. So if we are running a log search in a company, even if it's on premise, we could have like different indices. I put colors for the indices here. So we have the red index, blue index, green index, and so on. And the little shards of the index are spread among the different nodes. And yeah, it works. It works fine. But now one question that is interesting is how much does it cost? So if I wanted to size this usage, I would probably do something like choosing the kind of node that I should use. Elasticsearch has some kind of simulator for that, so you can like check it yourself how you should do that. But it will boil down to, if you use this node, it can handle this amount of terabytes, and so if you know that you have I don't know 100 terabyte and one node handles 1 terabyte, then you need 100 node, and it's that simple as that. And your node, it will be some kind of configuration with a specific CPU, some amount of RAM, and some SSD. So typically, like this sizing makes it so that you end up with a price which is linear with the number of terabytes that you will have to handle, and typically you will end up with a cost of around 1,000 per terabyte. So feel free to challenge this or do your own research. Everybody has a different figure for this. Yeah, so find your usually it's above 500 and it's below 2,000. It's the only thing I can say. It's not great because where is the the thing where multi-tenancy is cheaper. Like why don't we get like something that is getting like linear with a number of terabytes is good, but the terabyte should only be paying for the storage, right? Something feels wrong here. Having more tenants is not making things cheaper. So what if we could do a shared disk architecture? So I don't know if you guys are familiar with this idea, but it's something that exists in some exotic database. You have a shared disk, so something that will be like on the network, and your different server will take the data from the shared disk, run the computation locally, and yeah, that's the way it happens. So today, typically you could use an object storage like Amazon S3. And yeah, the idea would have to have a pool of searchers. This searcher would be stateless, entirely stateless, so they wouldn't have any data structure in RAM to run this, and they would be shared among the tenants. If we pull this, if we manage to do this, it's great, because when you have one index, it's not as if you query it all of the time, right? Think about your application service logs index. Only you and the 2 team member in your team are querying it. If there is 3 queries a day, it's a good day, right? So why would you dedicate a CPU just to handle it? And even if it's the other, if you were to look into the CPU usage of such a deployment, usually the index for your logs are spending CPU on indexing, and then after that search, but the main amount of time is spent doing nothing. So it's just wasted money. So this mutualization could really help a lot. And yeah, we dropped the SSD. The SSD is actually a big part of the original price. In comparison, storing 1 terabyte on Amazon S3 for a month only takes $23. So it's really, really low. If we just just to give you an idea, indexing 1 terabyte is probably less than $25, and the CPU for search, for log search, is probably less overall. If you have all of the queries that you run on your log search, it's probably less than $25 per terabyte per month. So overall, I believe that a normal log deployment will probably cost less than 100 terabytes per month, less than $100 per terabyte per month. Hence, 10 times cheaper than a regular log search deployment. So how would we do this? By the way, it's called separating compute and storage. So before doing it, we need to understand what the problem is. And S3 is a very strange beast. Usually when you consider the performance of some kind of disk storage, you consider two dimensions. One is the latency. So it's like when you try to read some piece of data somewhere in a file, how long does it take to get your first byte? A hard disk will give you something above 10 milliseconds. An SSD is very good at this. It's below 1 millisecond, way below 1 millisecond. And S3 is absolutely terrible on this axis. It takes 70 milliseconds to do a random read. The latency is absolutely terrible. Throughput, it's kind of the same story. SSDs are incredible. If you have an NVMe SSD, it will give you several gigabytes per second of throughput if you use it right. Hard disk, it's around 100 megabytes, and S3 is a little bit below that, maybe at 70 megabytes per second. So we are trying to do search, which is really IO intensive, with something that is absolutely terrible. So we've got some work. And we're gonna split it into 3 problems. So we have first, we want to run this multi-tenancy search with stateless search instance which means that when we receive a query, we have nothing in RAM. We need to open the index that the query is targeting and then run the query. That's already like a very difficult job. Usually when you send a query to Elastic, it's an index that is already open, and it has a bunch of stuff in RAM already, and it knows stuff about the index. We have to consider that we know nothing. The throughput is very bad, and we need to read stuff, so it's gonna hurt us a lot. And then we will have to deal with 70 millisecond latency, and I will explain why this is a problem in a little bit more detail in a few slides. So first, how do we deal with the fact that we need to open the index very fast? So to explain a little bit the problem, if you were to open an index on a TonTV index, TonTV has to open a bunch of files, and then it has to go and read a bunch of metadata at the end of the files. So you have some footer at the end of some files and sometimes some header. So you have to read a bunch of information here and there. And as I told you, every single one of these read, it costs 70 milliseconds. So it would be excruciating to do something like that. On S3, it will literally take minutes to do this. So what we do is after we have finished indexing a part of the index, we create a bundle. It's a file, a static cache file that contains all of this like little footer and little bit of information that are needed to open an index. And so when you send us a query, the first thing that we do is that we download this bundle, and it's only one operation of I/O to open the index. So opening an index with Quickwit, it only takes 70 milliseconds, even though we do that from Amazon S3. Now, how do we deal with bad throughput? Well, I actually lied a second ago. So I told you that Amazon S3 was like a very, very bad hard disk. It's not true. It's more like 30 very bad hard disk. So contrary to a single hard disk, you can do queries in parallel. You can do a lot of queries in parallel. It's actually recommended. And the only thing that will curb your performance is network throughput of your instance. And so in theory, you can get up to 2 gigabytes per second from Amazon S3. And experimentally, we do observe on very large queries that we manage, even though we had like this latency problem and we do have to run CPU and do stuff, we do observe that we download from S3 overall in average on the query at 1 gigabyte per second. So yeah, we haven't tried other object storage yet, but S3 is certainly delivering here. We are way closer to the throughput of an SSD than the throughput of a hard disk. So to manage to do that, we had to modify a lot the way we do I/O. Typically, something based on Lucene. Well, there are different options, but if it's using mmap, the I/O happens at the moment where you query the data. It's magic. It happens under the hood as you try to get a page from your virtual memory. And so it's the kernel that will deal with everything that you are doing. It's the kernel that will decide if it's a good idea to try to prefetch information and stuff like that. We cannot do that. So we change the way we do the I/O, and we change the data structure so that we can plan ahead all of the I/O necessary for a query, and we can run it in parallel and asynchronously and as fast as possible. And last of our problem, last but not least, we need to be able to perform the search and use our data structure in a world where every single random seek is taking 60 milliseconds. So I told you that we can do stuff in parallel, only to some extent, right? So sometimes you cannot do two read in parallel just because the result of one I/O operation is telling you where to read for the next operation. So you have this critical path of IO operation to run. It's like a chain, and you want it to be as short as possible. And with the usual data structure used in search, it's you're almost there, but you're not exactly there. So we had to modify the term dictionary, for instance, to make sure that we didn't have to do too much random seek to perform a query. And so once we have downloaded the hot bundle that I told a couple of slides before, we are 3 random seek from getting the result of our query, which is not bad at all. And then I want to talk about the other benefit of being stateless. We can add and remove server in seconds, literally, because like starting is just about starting a server and having it join the cluster. There is no moving shards around or anything. They are ready right away. Another thing that is interesting is so replication, the safety, the durability of your data is delegated to an object storage. So it's delegated on the possibly one of the most battle-tested technologies that there is out there. So I can sleep at night without any problem. By design, you cannot have a problem with your cluster having trouble or having to recover from something. It's in S3. It's those things that people use to archive their stuff. So I can show you a little demo. Oops. So can you guys see the logs here, or I'm not sure if it's if I'm sharing a tab or.
Oh, yeah, we can see the address bar as well.
So you can see the log app here?
Yeah.
Okay, cool. So yeah, it's simply a log search on, I think it's 40 gigabytes of logs, 130 million documents. And so I can perform a search. I don't know, I can do a filter on severity info. I've never seen a query that's that long, but that's an interesting demo effect. So it took 4.16 seconds, so it's not that bad. I can do different search. So you see that we can do aggregation and everything. The search experience that we have right now is entirely stateless. So I voluntarily removed every single cache that we have because we're not stupid. We do caching when we can. But it's interesting to make sure that that we can behave correctly when there is absolutely no cache. So can you see my window? My console here?
Yes, we can.
Awesome. So I'm currently running on only one search instance. So I'm gonna scale it up and see if we can get better performance. So it will take a little bit of time just because we need DNS to propagate. So the instances are already started. And the way we discover the different search instance is by polling the DNS every 5 seconds. So it takes 5 seconds usually. Should be about right. Okay, so now it's faster, as you can see. So adding 3 instances was just a matter of a couple of seconds, and I can scale it down. It will work just as well. So I'm switching on the instances. Yeah, we're slow again. So that's how easy it is to scale, and yeah, it's quite nice. Once again, there is no caching, so it does the computation every single time. So one last word about what will happen for Quickwit from now on. So Quickwit will be open sourced under the AGPL license. If AGPL is not compatible with business usage, then we will have a commercial license that will require to pay. And the first version that we will open source will be very simple. It will be just a CLI, and you should expect it for June. And we'd love to discuss with you if you have an interesting use case for us. I'm done. Do you guys have questions?
Thank you, Paul, for your impressive presentation. So now we can start taking questions. If you want to ask questions, you can just jump to the stage as well, or you can just leave in the chat. Anyone?
I have a question.
Great.
Hey, Paul, thanks for the presentation. It's been a while, man. I wanted to know more about the trade-offs for indexing and running searches. You've mentioned that you want to do that on different hardware because of the different requirements. And I would also like to know how the system handles index updates, because for logs in particular, you want to update your indices incrementally. So how are the updates handled? Thanks.
Yeah, that's a very good question. Who was speaking? Was it Sergey?
Yep, that was me.
Hello. Wait, we know each other. I didn't ask him to ask this question though, but we know each other. Okay, so you asked about what was I forgot the first question. So you asked what was the implication of running indexing and search, and I guess you were. I can explain the story about it's better to run them on different hardware, I guess. So it has to do to queue theory. Imagine that so it's a little illustration of people waiting at Starbucks. Imagine you have a coffee place where people come without any seasonality. So some amount of people will come within the day at any time of the day with the same probability, but they come at random and totally independently. If you have a lot of people coming, as long as at every single time there is someone in the queue waiting for coffee, you are sure that you are maximizing your profit as a coffee owner. So as long as you have clients at all time and the person at the cashier is never waiting and for customers, then you maximize your throughput. That's what you want for indexing. You want your CPU to never wait. But now as a customer, that's a very different question. You want your coffee fast. And if you are working in a workload that is that has that kind of saturation, so every single let's say that, for instance, you have as many people coming in a day as there are minutes in a day. They will come at any kind of random time. So of course, if they had an appointment for their coffee and it was perfect and they came at the right minutes, then you could have no waiting time whatsoever. But it doesn't happen that way in reality. So they will come at a random time, and so sometimes you will have like 3, 4, 5 people in the line, and you will have to wait a long time for coffee just due to this randomness. So if you are interested in the 95 latency of your query, you will see this kind of phenomenon happen, and you can actually simulate it. So it's actually a simulation of what happens if you have a load factor of what you have on the x-axis, and on the y-axis you have the time that you will be spending. And so if you are interested in the 90th percentile, you see that it like increasing your load factor by maybe a load factor of 0.3 is already like twice the 90th percentile latency as if you had absolutely no load. So it's really tough. It's really tough to have a nice latency when you have an important load factor. That's why you want to separate the hardware. Indexing wants a high load factor and search wants a low load factor. So yeah, I talk a lot. And the second question was, how do you do incremental indexing?
Right. The first question was about incremental indexing, because as far as I understand, the shard data is being pulled from S3, and that implies you access objects there, and you can only update the entire object at once, right? So that's reloading shards or adding new shards and updating the metadata so that it points to the new file. So I wonder what you're doing there.
Yes. So you know, actually, search is already working in a way where you, even if you use Lucene today, so there are exceptions to what I'm saying, but the basics is that it never modifies file. So you add a bunch of documents and it treats them as a batch, and it creates one piece of index that is supposedly read-only. And when you want to do updates, you batch them, and it's gonna create another set of files and remove the previous ones. So first of all, it already kind of works that way. There are some exceptions to it. So it handles deletes with a tombstone file, and doc values can actually be updated. But yeah, so coming back to Quickwit, we do exactly the same thing as what I just described. So when you add new files, basically it creates it takes a new batch of documents, and it creates a new piece of index that we call a segment, and it uploads that. So we do handle incremental search. We do not handle deletes today. So to handle deletes, we would have to update a tombstone file. We don't do that today. And so what we offer is you can deal with, so our main use case is things like logs where you don't have any deletes or updates of documents. What you want is just to be able to add new documents and then remove all documents. And so because we create like these small indexes that are very located in time, retention is actually very nice to deal with, because let's say that you have a 1 month retention, you just have to remove the piece of the index that are too old to be relevant. So you just have to garbage collect them when they are too old. So you download the entire files at the same time. Did that answer your question?
Yeah, thanks, Paul. I guess a quick follow-up here, like what kind of latencies for updates you generally get? I guess, of course, it depends on the data and like the settings for like how long of a batch you want to accumulate before you commit an update, but you know, maybe some numbers.
Yeah, so if we right now we only do really well when we receive a lot of documents. That's kind of a paradox in search. If you have a few documents, it's a difficult question. If you have a lot of documents, you can gather a batch rapidly and create your batch rapidly. If you have, so right now, if we have a lot of documents, we can create a batch every 30 seconds or so. And we love our ideal size of batch is around 5 million documents. So most of the time we cannot create 5 million document batches. So we create smaller ones. just to have a decent time to search. And then we merge them, just like you would do with, search is very close to an LSM tree if you're familiar with LSM trees.
Yep, that's the analogy I had in mind, pretty much.
Yeah, it's very similar. So it's the same problem, same trouble with merging and write amplification and everything. The big difference is that we cannot query the in-RAM data structure. So you have to wait 30 seconds or 1 minute or something like that to actually see your documents after you pushed it, which is not great, but not bad, depending on the use case. Is there other question? I actually cannot see the chat because I lost the window.
Yeah, let me speak it out. There's a question from Wanasit. If I understand it correctly, you are storing index segments as S3 objects instead of files. Is there any object storage feature, for example, schema, do you use? Or your abstraction is just key to byte array?
It's just key to byte array. By the way, hello, Wanasit. We just store them as files, and we rely a lot on the range queries. So object storage makes it possible to fetch a range of bytes. So we can ask like from byte 27 to 131, and we rely a lot on this. But we don't use any of the metadata. I don't even think I didn't know you could have a schema on object storage. We don't use any of that. So right. we have an abstraction actually for the storage. We are meant to be used on object storage. So like Amazon S3, of course, but in the future we will handle the Google one. I forgot its name. The one in Azure as well, and even it makes sense to run on HDFS as well. The only thing we require is to be able to put, get ranges of the data.
Good. Hi, Paul. So follow-up question to that. So does it mean that basically you need like key value storage to store like that byte array in the database instead of as a file? So in theory, you could use any database, right? It doesn't need to be object storage. You could store like segment as a row in SQL database if you want.
Yeah, we could, but usually like storing a big blob in a database is not very efficient, but we could store an entire and also I guess database usually maybe I'm wrong on this, but usually if you store a blob, they will give you back the blob entirely, and we want to be able to fetch ranges of the data. So we want to be able to fetch ranges of bytes, not the entire stuff. We never download the entire stuff because it will take too long.
I see. So I didn't know that you could, when you stream from object storage, you can end early. You don't need to download the whole object.
Yeah, you can send HTTP range queries.
I see that.
And it works, yeah.
Cool. Thank you.
Do we have any other questions?
Well, since nobody is asking questions, I have another one.
That's good. Sounds good.
Could you touch on like achieving consensus on what the current state of the indices is, right? Because we have like multiple servers that do the actual search, and they have to agree on what the current generation of the index is.
Yeah. So Okay, yeah, I didn't, it was a very short talk, so I did not explain much about how, like the architecture, what it looks like. So the way we do stuff is we currently we rely on a message queue to get the logs to index, and then you've got an indexer that index the message queue, and once it creates a shard, it uploads it to S3, and after it's uploaded to S3, it will just create a transaction to a SQL database to publish the split. So it's gonna say, okay, the split is now available, and so all of the search server, they have to call to discuss with this metastore, this central metastore that is handling this state. So we are cheating there, basically. we are relying on a SQL database for the meta of the index. So the generation to hit on is it's actually sitting on a MySQL. So that's what we do for the demo that you've seen, and the first version that we will publish as open source. It will be different just because we wanted something very simple to deploy. The metastore will be just a file on S3, and so we will rely on S3 to do that, which means that the search server will have to fetch the data from S3, and maybe they might do some caching, and in that case they could be lagging a little bit behind. So when you send your query, the server you send it to will be in charge of the coordination, and it will be his version of the metastore. If it's cached, then it might be lagging. It will be his version that is used for the entire search query, because it will be the one that will be in charge of dispatching the work between the other searcher nodes.
Gotcha. So it's an AP system. Thanks.
Yes.
It looks like so Francois is your friend?
Francois is my co-founder. Yes.
I see.
So yeah, I have a bunch of actors in the crowd to ask questions and clap at the right time.
So does Francois want to jump to the stage to say something as well, as a co-founder of this company?
Yeah, yes, of course. Thank you, Paul, for the presentation. That was very interesting. Maybe it was very short because we may have many things to say more. So don't hesitate to reach out on Twitter or by email at paul@quickwit.io. We'd be very happy to continue conversations on this.
Yeah, especially people from Indeed. If you want a search engine for job archive, please let me know.
All right, so that's the end of our Q&A session, and we're gonna have another session for networking. So if you want to stay to interact more with the speaker, feel free to stay. And if not, enjoy the rest of your day. That's all about today's meetup. Thank you for coming.